Oh, my ear harmonica's going. All right. Ah! Wake up. It's morning. Ah! Geez, this is like seeing the sunlight. All right. Ladies and gentlemen, here I am. Watchwell is my name, and natural philosophy is my game. And for those of you that have seen the show before, always remember that the emphasis is to learn something. And now that we are clearly into the autumn, I've been getting a little bit more into the kind of the academic spirit, because now my youngest daughter is in high school and my older daughter's in college, and even my youngest daughter's in second grade, and she's busily learning mathematics. So I tell you, my brain is just churning here, trying to help them and trying to help you and everything else. So we're trying to have a little fun. So I have these different problems I've been going through. So I'm going to try to share a few with you today, and they're like kind of kinky. And then also, they're kind of like velocity problems and distance problems, the kind that everybody gets and hates. And also, I'm going to try to do an extended version of the Where Are We segment, because now we are into a new month. We are now into October. This is the 6th of October that this is being shot. And so I try to get out the shows when I can, but sometimes I can't always do it every 2 weeks. I try to, but sometimes it's difficult. So here we are down in the basement of we're at Channel 10 in the basement of City Hall, and we got lights and everything, and we try to make things look like it's a classroom. But in reality, ladies and gentlemen, we're kind of in the studio here. But in front of me, I have hundreds of young students that are looking out for me. But anyway, so what we're going to do today, is we're going to try to. I started a problem about distance, and I'm going to second think that one, and I'm going to go through it a little bit and do a couple easier ones leading up to it, and then we'll try to get for that hard one, because it gets a little harder. But the premise is, and what is that you get these like problems. Like I got my old math book here. You know, they always say there was an old book once that said everything you ever had to learn about life, you learned in kindergarten. And so I guess I could turn it around if you want to put that in the kind of like the science mold or something. You could say, well, everything I ever wanted to learn about higher mathematics, I learned in my 9th grade algebra class. So if you go through this baby from start to finish, there's always so much in there. And there's all the problems that everybody hates, you know, like the age problems, you know, and the work problems and the distance problems and geometry problems, you know, all the ones you hate, like, you know, right, John is a quarter of the age of his father, and in 5 years, his father will be only twice as old, and all those that drive you nuts. So what's difficult about a lot of those problems, the algebra problems is, well, you got to learn to manipulate the numbers, but then also it's kind of hard to oftentimes visualize. So I personally, Watchwell, I'm always a firm believer of the concept of a picture is always worth 1,000 words in solving some of these problems. And so in solving some of these problems, I was reviewing some of my old dynamics. Actually, there was something else I was analyzing, see, and so they show some ways to try to help, you know, draw like little pictures of like little linear things, and it helps clarify that. And so I'm going to try to explain some of that to you that maybe will help you, see, because my goal is like kind of like as to the world, if I can help even one person to understand something a little bit better or think of something in a little different way, then I was doing my job, see, so that's what it's good. Okay, so that's kind of a setup here for the show, and we'll just have some fun as we watch. Like I said, we're into October. Also, I'm just kind of spieling away here. Of course, watch on the screen that we have our program times in the P.O. box in case you have any kind of information. So the one that I had last week, I'm going to kind of verbalize it quick, but then I'm going to do a couple easier ones, because this one actually was maybe a little bit, well, it's not really hard. It's not hard if you're in school taking a class, but it might be a little hard for public consumption. It gets into quadratics and gets a little more involved. So maybe I'll save that one for the end. But this one, it was kind of cute. It was kind of like, I set this up just before I left, is that as I was just finishing up, I ran out of time. And it was kind of like a drag racing problem. It was like, there were two cars that were sitting at a stoplight. See, like right here, you know, lined up. Like, think of it like drag racing, like they're so queued up and they're ready to go. And then the light changes, and then the one guy, car number A, he starts taking off at a certain speed. And then car B, something happened. Maybe his car choked out, or he was, whatever, turning off his radio or something. But for some reason, he didn't leave the line here till 2 seconds later, and he's going up. And then the whole problem is that if this one leaves at a certain acceleration, this one leaves at a slightly higher acceleration, which means he's going a little faster. It's like, how long does it take to catch up with him, and so on and so forth. But that one, again, it ends up being just a little bit more involved. So what I'm going to do is I'm going to kind of do a couple easier ones leading up to that, and then I'll do the Where Are We segment, and then if we have time, then we'll come back to that one. Because again, this is kind of like I appeal to a general audience. My audience is everything from 7th, 8th, 9th grade, high school, college, to people who went to school, people who wanted to go to school, people who wish they went to school, people who went to school and wish they would have done better, people who went to school and did good and now they're bored. I mean, it's like, it's the whole gamut of people I'm trying to reach here. But before I get into my math and stuff, let's have a little bit of fun here. Lately, I've been listening to Michael Savage, who comes out of San Francisco, and KSAN out of San Francisco, AC. He is so funny. He's got a book out now. It's called Liberalism is a Mental Disorder. And he is the greatest guy. I love this guy. I used to listen to like Windbag and stuff, but he is so good because he doesn't carry water for any political group. He just talks about human weaknesses and human frailty, and I tell you, he doesn't pull any punches. He's pretty good. He makes fun of everybody. He makes a lot of fun, especially Windbag. He calls him Rush Bimbo. He makes fun of everybody. He's pretty good, but he's a little coarse if you listen at the beginning, but he's actually pretty erudite, and if you could take the truth and you're not afraid of the truth, he is the guy to listen to. That's all I can say. He is the guy to listen to. So, listen to Salad. Okay, so now let's do a couple of these little problems I'll talk about. Now, what we're talking about is, again, these distance problems. Again, they're kind of like, the age problems and the distance problems and so on and so forth. So this is going back to my 9th grade algebra. Man, that was so many years ago. I'm fearful to recollect that far back. But nonetheless, back to my old algebra days. And this is, again, these are like the problems, again, that you hate. But so this is called, there's various types. One's called motion problems, work problems, age problems, coin problems, geometry problems, I'll give you a quick example. Again, these are the ones that you hate, but I'll read one. Like here's the kind that you hate. It says, a man has 2 more nickels than dimes. He has $1.15 in all. How many coins of each kind does he have? See, those are kind you solve in 5 minutes. But again, I'm not making fun. This is a 9th grade algebra. So this is not quantum mechanics here. So let's have a little fun with it. So like I said, I'm gonna do a couple easier ones and then lead up to some harder ones. But what I'm trying to stress here is understanding some pictures that go with it so you can get a little better understanding. So here's a kind of a good one. Okay, and here it is, kids, the first one problem here. It says 2 trains start at the same time from 2 towns 385 miles apart, and they meet in 5 hours. If the rate of one train is 7 miles an hour less than the other, what is the rate of speed of each? Okay, I'll read that again. Okay, 385 miles. So picture 385 miles. What's a good picture? Picture St. Louis. There you go. That's a good one. Picture St. Louis from Chicago. There, that one you can kind of visualize. All right, there, that's simple enough. Okay, Chicago's over here and St. Louis is over here, and let's just say, so at least you can get, in nothing else, just make the connection, okay? So we're just saying, so what they're saying is it's 385 miles. It's whatever. It's two points, whatever. Salt Lake City is 385 miles from Denver or San Francisco or some point. So we'll just say that St. Louis is 385 miles from Chicago, just so you make that connection, that you're talking about a particular line that you want to fill. Okay, so two trains are leaving the stations, and they're heading toward each other in a distance of 385 miles, and they meet each other in 5 hours, and one train is going 7 miles slower than the other, or one train is going 7 miles faster, depending on how you look at it. So the secret of doing these things, again, is, they're telling me where to look here, is you got to start drawing pictures. That's how you got to do to understand this stuff. You got to draw pictures. Draw pictures. So here's how we're going to set this baby up. Now again, this is not that hard. This is 9th grade stuff. So we're going to have these two trains. Okay, they're sitting over here. So this is going to be whatever, city A, and this is going to be city B. And we know the distance. We know the distance is 385 miles. Okay, when they start. And then one train is going to go that way. And one train is going to go that way, and then they're going to meet each other. But now we have to do the algebra. So it says the time involved. So when we know the distance, that's S. S means distance, 385 miles. And the T for the time is equal to 5 hours. Okay. And then again, that's easy enough to visualize too, right? If you jumped in your car and it took you 5 hours to get to Chicago, you would say, well, the time involved would be 5 hours, and the distance would be whatever, 270 miles or something. So here's, I'm just going to go through the algebra kind of fast, but that's the idea. Okay, so what you want to do is you want to establish two things. Okay, you want to establish, be able to take the time and link it with a distance to end up with a velocity. Okay, that's the key point here. Now, as a setup, to understand this a little bit, certain of the distance problems, there are certain key formulas that you have to kind of learn somewhere along the line, okay? And in this particular case, S equals to VT, okay? And this is like a very common stuff you get. Everybody gets this like in about 9th grade algebra and the science, you know, where you get the distance is equal to such and such a thing, or the gravity formula is the distance is equal times acceleration times the time squared over 2. But this, we're going to do the easier one. So this is like a very common formula, is that distance is equal to the velocity times the time. And that's kind of a no-brainer. What that means is that if you're going 60 miles an hour and you continue to go 60 miles an hour for 1 hour, in other words, you're on the freeway going from here to Madison and you don't slow down and you don't speed up, in 1 hour you would go how many miles? Well, clearly the answer is 60, right? 60 times 1 would be 60. Okay, so that's not that hard, right? Okay, so, but where this one gets a little tricky is what we have to do is establish the velocity and the time. So they said that one train is going 7 miles slower than the other. So here's where we got to do a little kind of trickier algebra. Okay? And again, I'm going to go a little bit fast, but once you see the idea that if it's all based on this formula, then all you're really doing is substituting. Okay, and so what we're saying is, we're going to say, we said this was train A, and this was train B. Try it again. One from train A, and one from train B. So train B, we're going to say B is equal to, velocity of B is equal to VA, train B, minus 7. Then we're going to put that in a bracket so we can manipulate that, okay? And then we know, ladies and gentlemen, that the time is equal to 5 hours. So here's where it's tricky. So what we are saying then is that the velocity minus 7, this quantity over here, times 5 hours, plus VA, just VA by itself, that's equal to VB, times 5 hours equals 385, see? And then that's the beauty, is that then you solve for A, and then once you solve for A, you just minus it by 7. So then you solve this, so then you know how to do this. You multiply this VA times 5, and this becomes minus 35, VA. You combine, and you crank that baby down, and you solve this. Again, that's not that hard. A little algebraic manipulation, and you get the answer of 42, okay, equals the velocity of A. And then you go back to the original premise where you said the velocity of B is VA minus 7. Therefore, 42 minus 7 equals 35. And then that would equal the velocity of B. So then, see, it's not that hard. So then we have solved that 42, velocity of A of one train is 42 miles per hour, and the velocity of the other one is 35 miles an hour. So again, what I'm saying before is that, okay, so you can grind through these numbers, but if it's all just numbers, it doesn't really quite smack you alongside the head, okay? So here's what I'm going to say is that I was studying in this other book, and they were showing how you can take some of these pictures algebraic manipulations and make them into pictures, and then it helps kind of clarify the issue. So how it works is in the following way. Is actually for the sake of making so I can follow my same picture. Let's say let's go like this. Go back to my original thing here. We're going to say like this, and I'll explain like this, like this, like this, like this. There we go. Okay, so the time goes that way. The velocity of B, of course, we're going to have to say is velocity. We're going to call this train A over here and this train B over here, just so it comes out the way I drew my picture. And then we're going to say that this one leaves the station going 42 miles an hour. And then, of course, for it to make sense, we'll say it's in a negative direction, because just like Cartesian coordinates, positive numbers are this way and negative numbers are that way. So it goes that way, and then this one goes the other way. And VA is going to equal to 35, okay? So you multiply it out, and then they meet. And if you know that the total is going to be 385, then I cranked it out. So it turns out that if you go through that time business, that this one train here, the one that's going faster, translates or traverses 210 miles, and then the other one going the other direction is like 175. And then you could take the same thing, so then you have the distance and the time. Go back over here, the distance and the time. So you know the total distance and the velocity, and you can divide it out. Then you can get how long it took that train, to go 175 miles, because you know the velocity. And then this was the distance, so you can get the time. So it's such and such a time 1 equals this, and such a time 2 equals that, and then that equals 5 hours. Now again, I'm going a little bit fast, but just the idea is I'm showing you that you can draw a picture, and so then that ends up being what you would kind of call the area or the integral. So it'd be 210 miles by that velocity would yield so much time, and then the same thing occurs here, and then this would be not 42, but would be like 35. Again, so you could visualize it kind of like 2 boxes. And then as you multiply it out for your units to come out, remember I always said that no matter what kind of problem you're working with, the units will always come out. And indeed they will, because in this case, the distance is equal to the velocity times the time. And so the velocity is saying miles per hour times some time in hours, and then the hours go away, and then you're left the distance. So it makes sense. So the other train going 42 miles an hour translates or transverses 210 miles, and this one going 35 miles goes 175 miles, and then they meet here, and then this distance and this distance together equals 385. Whew. Okay. Now that's the idea. Again, getting a little, I try to keep it simple, but then yet you have to be complete enough to get the whole thought, but there are a few holes in there, but it'll maybe give you something to work with. Now I'm going to do one more quick one, then I'm going to do the where are we segment, and then we'll see if we got time to get back to our drag racing problem. Okay, now that's a little kinky again. Now, see, Watchwell is a little more advanced. Now, when I did this problem, I just read it through, and then I did it on like one little piece of paper, and then I scribbled this stuff out here, and I did this in about, for me, it took about 3 minutes, but of course, because Watchwell has been doing this kind of stuff for years and years. But anyway, so even if I simulate even one person in this audience, I will feel that I've done a better job. Okay, now let's see what time is going here. Oh boy, time always goes too fast for me. All right, now I get time to do one more. And there's another one. Now next one's a little bit more fun. I'll try to get 2 of them out if I can. Now this is another one. Now this one, the second one came out of a dynamics book. Again, I had this book down here last time. This is a college textbook, so now we can go fast forward. And this actually was from a course I took at Marquette years ago. And now, so this is now you're into kind of college stuff. So then we're kind of fast forwarding. So then the one who kind of got the stuff of the last one, this is maybe something you could kind of sink your teeth into. Okay, so now here's one that you can kind of relate to. Okay, and I'll knock off this one, then I'll see how much time we got left for the Where Are We segment. Okay, it says, this is another problem I can do, and I'll try to draw a picture. It says, a police officer observes a car approaching at an unlawful speed of 60 miles an hour. He gets on his motorcycle and starts chasing the car, just as it passes in front of him. After accelerating for 10 seconds at a constant rate, the officer reaches a top speed of 75 miles an hour, and the question is, how long does it take him to overtake the car from the time he started? Now again, these are a little abstract, so they're not that easy. So let's try it again. Okay, I'll read it again. Okay, so a police officer observes a car approaching at an unlawful speed of 60 miles an hour. So must be a 35 mile an hour zone or 45 zone, and it would be going 15 over the limit, say. It says he gets on his motorcycle and starts chasing him. Just as the car passes, so the cop is sitting there and the car goes back by, okay? It says after accelerating for 10 seconds, that means he's still, and then he's getting up to speed, and then he starts to flatten out at 75 because the other guy was going 60, and it says how long does it take him to overtake the car? Okay. So again, what we'll try to do on this one is we'll try to, again, a picture is worth 1,000 words. Okay, so again, I might be in over my head here, but let's hope that somebody gets a little something out of this. So how we're going to draw this one is, again, we're going to draw two pictures there. Two pictures there, hey, okay. Picture of lemonade, no, picture, okay. So now on the first guy, well, car A, or the speeder, okay, he's going 60 miles an hour. Yeah, which one looks a little better? See, let me stick with the pink here. I think it'll look a little bit better. Okay, so the speeder is going 60 miles an hour, and then it's constant. See, he's not speeding up, he's not slowing down. He's going just constant. He's at 60 miles an hour, he's going boom, 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 boom. And the cop is sitting still, because the cop is sitting there, but he apparently has a radar gun or something, so he knows that the guy's coming down the pike. So the other guy's just going, and then right, again, if you look at it from the top, so the cop's got a radar gun or something here, the car's coming this way, and then the cop is sitting here somewhere, and it said right as the car passes in front of the cop, at that instant, then the cop goes and starts chasing them. But again, the cop is still, see, this guy's going 60 miles an hour, he's like 88 feet a second, so he's going zoom, so he's moving. So the cop, it says that the cop accelerates for 10 seconds. So the cop gets on his bike, so his velocity, again, we're setting it up here, it's velocity and time, that's the idea, see. It's velocity and time that we're trying to be concerned with. Velocity or speed. And the cop is not going at all because he's sitting there. So then it said that he accelerates for 10 seconds. From here to here is 10 seconds. And then he says he gets up to a top speed of 75 miles per hour. Okay, so now we can, by intuition, we can say, well, 75 miles an hour is faster than 60 miles an hour. So it takes him 10 seconds. So he must have a pretty strong machine. So it takes him only 10 seconds to get up to speed, 75 miles an hour, which is 10 miles faster than you can legally go on a speed limit. So needless to say, the guy's got a pretty good machine. So the key of the whole question is the cop catches him when his area underneath the curve is the same as the other guys, okay? And so it's like this. So in 60 seconds, this guy goes some distance, right? Because it's a velocity. Again, back to our distance business. Velocity times the business. But distance times the velocity. We know the velocity times t. And we want to know how long it took for the cop to catch him. Okay, that's the whole idea here. So, and then this one, of course, he's sitting still. So then there's two things. So then we have kind of like an area 1, or this distance here when he's accelerating, getting up to speed, and then you have this distance over here. And the beauty is that in this distance here, when you crank it all out, when you take the 10 seconds and you go through all the formulas, it turns out that in this distance over here, he goes 550 feet in his accelerating phase, and then he goes 1,650 feet in his constant speed phase. And then meanwhile, the speeder, just by going from 60, it's keeping it at 60 miles an hour for such and such a time, he traverses 2,200 feet, which is like about a half a mile, like 1,330 is like half a mile. And then he goes over here. And then when you put the two together on those, using those two little formulas you have to use, it turns out that it ends up being 25 seconds, okay? So that is the idea, it's 25 seconds. Now, I don't want to do all the algebra on that because it gets a little more involved. But that's the idea is, you got a hinker and dicker. But if you can visualize, again, if you can visualize kind of like comparing areas, then that helps you understand the numbers. So you use this area, this S times this VT to figure out this. And then this one, of course, you had to figure it out in two parts, because in this one over here, you had to use the distance is equal to 1/2 times the acceleration, you know, t squared, okay. Then you have to do the acceleration, get that over here to get this distance. And then once you get up to speed, then you have to work backwards and subtract the remaining amount. And then you add those two together. That gets a little bit more involved. Again, sometimes if I get too academic here, it gets a little kinky. I got to watch my time here. Okay, I think I'm going to have to postpone my where are we thing until next time. We had fun going through our distance problems. Watchwell is my name. Natural philosophy is my game. And until we see you next time, kids, bye-bye. We'll do an update of the planets. When we talk next time. See you later, alligator.